We have a really interesting makeup for the panel. We'll have some impressions from system operators that are already dealing with really high shares of IBR. So they'll talk about challenges that they're seeing on the grid. And then we have a presentation that is summarizing a survey of needs for different stability simulation tools that people are seeing as they increasing shares of IBRs on the grid. And that's followed by a framework of how to look at stability services that are needed in the systems with high shares of IBRs. And closing out, we'll hear about small signal stability analysis. So this is kind of one of the tools in the toolbox that's being needed as we're getting higher shares of IBRs. So without any further ado, we'll start with John Phipps from CAISO. He is Executive Director of Grid Operations there. Go ahead, John.
Thank you, Julia.
Yeah.
All right, thank you guys very much. It's an honor to be here. I've been with California ISO for nearly 25 years, so I've had a chance to see a lot of the evolution of the California grid and the Western grid and the California markets. So I'm here today to represent the Balancing Authority primarily in the discussion of the IBRs, although California ISO does perform the Reliability Coordinator function and also the market operator for the Western Energy Imbalance Market. The California ISO Balancing Authority we have about 32 million customers. Our peak load was set just 2 years ago. So even though California does have a large concentration of rooftop solar and even behind the meter storage, we have set a new peak record just 2 years ago. So we are seeing the load come back. For a little while there, we saw the peak load drop, but it is coming back. And we, as of this year, we have about 1,100 unit power plants. Probably 5 to 7 years ago, that was around 7 to 750 plants. But you'll see that in probably another 5 or 7 years, that'll be up to 10,000 plants. And so that's one of the challenges I'll talk about shortly. Just some brief stuff on California Balancing Authority. I really just want to hit the top two on the renewable generation capacity. Nearly 20,000 megawatts of solar, 8,300 megawatts of wind, and as of just October 1st, 10,200 megawatts of storage. So the storage, we've seen roughly almost 6,000 megawatts of storage added in the last year. And this is some of the stats, and I just wanted to really, again, hit here 2 of those. With that 20,000 megawatts of solar, we did hit a solar peak this year in August of 19,650 megawatts. So we're actually seeing that solar production actually hit the grid. And back in February of this year, before we hit our peak solar, we did have as has been talked about in some of the other presentations, with the large concentration of solar, if you're looking at net load, it displaces a lot of the traditional resources. But so then in the evening when that solar ramps down, then you have to replace that with other resources. And we did have a 3-hour ramp of over 21,000 megawatts within 3 hours. So a lot of ramping capacity has to be installed and available, not just megawatts, but actually megawatts per minute. Because we have had situations where we had an hourly good amount of energy, but it was moving too slow. And even though I was good for the hour, within 20 to 30 minutes, I had a very large negative ACE and was having challenges maintaining the grid. So I'm going to just hit on some of the operational challenges. I talked about the large solar output. It is displacing other resources, including hydro. So we do need sufficient ramp capacity. Storage is beginning to fill some of that during the middle of the day, as has been discussed. It's a good time for the storage to charge. And since we have around 10,000 megawatts of storage on the grid, we do see for about 6 to 7 hours, we're seeing roughly 5,000 megawatts of battery charge for those hours in the middle of the day. And so then they are available then in the evening to kind of replace and backfill solar that ramps out. And I have a little chart where I can demonstrate that. One thing we saw early on was the reduced frequency response with the large growth of the solar fleet. The wind was coming on some, but we did start to see a degradation in our frequency response. We actually, in order to protect the grid, we actually paid others to help provide frequency response for us. So in a sense, sold our frequency response to others or paid them to take it. But now with the batteries being added, we've actually have some of the best frequency response we've seen in 10 years. So battery is able, we worked with really the inverter-based resources as a whole, solar, wind, and batteries to reprogram their controllers. Initially, they were programmed to connect more to a distribution system than a bulk electric system. So they weren't really responding as expected. So we met with the community over a couple of period of years. Many of them could reprogram the controllers to actually provide voltage control and frequency response. And so now, as of this year, we have, like I said, some of the best frequency response we've seen in many years. Another one of the challenges was a lot of these resources coming on are not traditional, industry traditional companies. A lot of financial institutions putting inverter-based resources on the grid. They just want to get it on, connected, and then commercial. There's a lot of processes involved to get a resource commercial, as I'm sure you all know. And sometimes, depending on the issues they had during development and construction, they could be running late. And they still want us to have them go to commercial due to financial obligations. But also what we found was a lot of the operators of these plants really had no idea what they were doing, and many of them actually did not even have control of the plant. They would be located remotely. We would call them and ask them, we would have transmission overload, and we would have tried to decrement them or reduce the output, and they would not respond. We called them and they said, well, I can't control my plant. So we've actually had the transmission operators actually de-energize the line to the plant just to get the reduction in that output, but we have been able to work on that as well. And another challenge as we began to work with getting these resources going commercial, we would train the operators of what they needed to do to communicate the test levels they would be at for each hour, so we could know if a battery was going to go, say you had a 200 megawatt battery, it'd be full charge and then want to go to full discharge in a matter of cycles and would see 400 megawatts on the system instantly. We had to be prepared for that. So we worked with them to communicate better, but as soon as they got it to go commercial, they hand the keys over to the owner. And now there's a new owner that walks in, has got a shiny new resource, and they start doing the same behavior. They don't really know how to behave because the owner is also not really an industry typical owner. But so we've had a lot of communications and trainings with all these resource developers and owners. And as I mentioned earlier, the inverter settings, we were able to get a majority of the inverters and digital control systems within the California BA footprint to reprogram them. So they do provide very good frequency response, even wind and solar both can do that. And they are also we had issues with some cessation on some of the wind and solar. If there would be a 500 or 230 kV line relay, the programming at the time, again, distribution system saw a voltage dip. I was using the voltage to calculate a frequency, and it saw a frequency drop below its programming, and it would actually shut down the plant. And so we'd lose a line, and then unexpectedly miles away would see a plant trip off or go to zero. They didn't even trip. The breakers are still closed, but they stopped producing. So we got them to reprogram the controllers for that as well. There's been some talk about the net demand. And again, this chart here is from the day that we had the 21,000 megawatt ramp. So you do see the gross load at the top, and you can see that the net load approached zero on that day. So we actually did have enough wind and solar, the biogas to serve 100% of our load, but we do have minimum online requirements for a lot of our generation. So we actually export a lot of this or charge batteries. But you can see that California does for several days of the year and for periods of an hour, more than 100% renewable compared to our load. So it is here, and it's a little scary, but it's also impressive as heck to see the grid staying stable and getting better. This is our battery storage. So as I mentioned, we just hit 10,000 megawatts a little bit ago, and I apologize, the graph is off because I resized it. But in the third quarter of 2024, we did hit 10,000 megawatts. So that little dotted line is off. But you can see by the end of next year, we're supposed to be at around 27,000 megawatts. We're going to nearly triple our battery installation in 1 year. And so again, this has been mentioned in some of the presentations. When you have the large solar, you actually get curtailment in the middle of the day. So you actually are wasting renewable energy. But now with the addition of the batteries, we can actually capture that and then release that in the evening or even in the morning hours. So the batteries are coming fast, and now that they're hitting the grid, we're learning more and more about how to manage them. At first, it was a little hairy. But also we're seeing that with such a large battery installation, they've displaced our traditional resources that supplied our regulating reserve. We used to have a lot of hydro and the multi-stage or the combined cycle plants that would provide our regulating fleet, and 90% of it's now battery that provides our AGC regulation units. So they respond very well. They're faster than hydro. We actually have to program our AGC system to slow them down because they will move faster than the rest of the fleet on the grid. So, but they do very well. So they actually really have increased our, I would say, reliability and stability. Here's an example. I'm hoping this shows in the back of the room. It's actually a trend that shows our old duck curve where the solar hits the minimum middle of the day. The solar's high, minimum load's low. And the red line is now showing with batteries how we've been able to flatten that duck curve out a little bit. So as more batteries hit the grid, we have less of a climb in the evening. So the batteries really are able to take that duck curve and flatten it out and make it be more manageable. And this is a demonstration of our frequency response since 2017. And you can see on the left, in 2017, it was 250 megawatts per hertz, 0.1 hertz. It had been degrading and degrading, and it's been watching that. And like I said, we actually were paying others to take a part of our frequency response obligation. But since 2020 and the battery starting to hit the grid, our frequency response is now better than it was 5 years ago before we really had much solar or wind or battery. So storage really is helping, as well as the programming on the wind and solar inverter controls. There's still a lot of challenges. We have a record number of new resources coming. Like I said, we'll have over 10,000 resources in just a couple of years with the large addition of batteries and continued solar and wind growth. I have a bunch listed here, but other ones that I don't have are information overload for the operators in the control room. An operator, we were able to kind of manage 700, 800 resources, individual resources. We had them aggregated into different groups. But when you get 10 to 11,000 individual resources, it's impossible to really monitor all of them. So we are trying to figure out how to create smarter alarms, maybe even start to use some AI to identify a behavior that's outside of a parameter, so we can quickly find the resource that might be doing that. It's also, if there is errors in that resource, that's what it becomes now. We used to manually replace the value in our EMS system to what we knew they were at. If you got this many resources, how do you do that? And we have to keep accommodating the testing of all these new resources. And so that's resources that are not being optimized in our market, but are coming on and charging or discharging outside of the market. A lot of transmission upgrades required. I won't go into that too much. That's been a topic of a lot of discussions. The unfamiliarity with power system operations by the plant operators or the owners. We have a lot of some of the scheduling coordinators that manage the resources for the owners are not even in California. Some aren't even in the United States. We have some that are internationally located control rooms, and they remotely operate the plants. So sometimes our requirements may be different than what New England or New York have. So trying to make sure they understand our requirements is an issue. That's really the big part. I just have here, if you want to see, we do have an ISO Today app that you can get on your phone. And some of the graphics I had are actually straight off the app. And then we put a lot of data out there and it's historized. So if you wanted to see what we did a year ago, 2 years ago, you can go onto that specific data point you're looking at. And there's a calendar that lets you pick the date and you can download the data. But this one was actually just from Friday. I took the screenshot here on the today's app. So it gives you some pretty good details. And if you click on the boxes, it gives you a lot of detail. And that's the one on the right. On the left is our website that has similar data. It's just, for non-app users. With that, I will end it and hand it back to Julia.
Thank you, John. I think we'll take all the questions at the end just to make sure we have sufficient time. Before we proceed to the next speaker, I wanted to make one announcement. At 5:30 to 6:30 today, before the main reception, there is a reception for students and young professionals. So if you're feeling like you're in your 20s, come to the reception 1 hour earlier and mix and mingle with other young professionals and students. All right, so next on, we continue in conversation about from system operators that are experiencing high shares of inverter-based resources. And we have Xiaoyao Zhou from National Energy System Operator, and he's an engineering compliance manager there. Go ahead, Xiaoyao.
Hi, afternoon, everyone. I'm Xiaoyao, so I'm trying to today give a talk on how we actually operate the system with a lot of the renewable generation connecting the system. Oh. Right, as Julia mentioned, that we recently become an independent system operator. We used to call National Grid ESO part of the National Grid. Now we become an independent system operator. But name has been changed, and rather than the electricity system operator, we actually become National Energy System Operator because we take some of the additional roles from this new organization that doing the whole energy system planning, not only limited to the electricity system. So when you're looking at the whole GB system, so we have a different TO in the different area. So for the NESO, we're operating the whole transmission system. And not only that, we're also doing the operational planning, making sure that all the power is supplied all the time. So we managing the customer connection process as well. We come up with a recommendation for the long-term transmission investment as well. And apart from that, we're also doing sort of technical code development, making sure that all the people connecting to system have the right technical requirement. At the same time, we develop a market framework as well, making sure we actually procure the right ancillary services to making sure we can run the system reliably and economically. So how the GB system evolves, and the GB system in the past is that we have a lot of the traditional generation in the system, so coal-fired power station, a gas power station, nuclear power station. In the last 20 years, we've been through the very rapid journey to decarbonize the whole electricity system. So we have more and more renewable generation connected system in the form of the mainly offshore wind farm and the PVs and battery connecting to the system. And in the last months, we actually decommissioned our last coal-fired power station. That's in the since Industrial Revolution, 184 years. If I remember the number correctly, we are running the GB system without any of the coal power firing station from the supply the energy to us. That's a kind of like a very big achievement. So we're not stopping there. And as you can see that from the left, we have currently where we are and what we are going to be in a few years' time in the next 10 years. So we have a more and more renewable generation connecting system, offshore wind, PVs, and battery. So that's actually imposed quite a big challenge for us. That's on the right-hand side, that's one of the longer-term transmission configuration or topology might looks like. As you can see, there's a huge amount of their offshore wind will be coming to the system. They will be connected to the system through the meshed HVDC network into the system. So in the future, we see our GB system looks like you have a AC and DC running in parallel, and we have a lot of the IBRs connecting to the system. So that's probably posed a lot of the operational challenge for us. So when we're looking at all the operational challenges, some of them are fairly traditional, like you might have thermal limit that you need to build enough transmission capacity to connecting all the generation into the system, because your demand is generally getting lower as well. So you might have a high, very lightly loaded transmission system. So you're starting to see the high voltage in the system. And the frequency is quite an interesting one because you have less synchronous machine. So you starting to see less inertia in the system for in-feed loss or generation tripping from the system. You're starting to see frequency changing much, much faster than before. So we have to deal with that issue. For stability, that's quite an interesting area because when the IBR connecting to the system, they're starting to impose different stability challenges to the system. It's quite different to the traditionally what we see as transmission or sort of transient type of the stability issue or the low frequency oscillation type of issue. So let's just give you some examples to see how the system actually changing. We can clearly say that inertia has been changing massively. I mean, since the last 10 or 20 years, we also starting to see the system strength, or as measured in fault levels, has been decreasing in the future as well because of the IBRs generally generating much less fault current during the fault compared to synchronous machine. So what we're actually going to do to tackle the challenges, one of the things we're thinking is actually it's fairly important to looking at in a very structured way. So one thing you're looking at, so what actually system needs in the future when we have a more and more IBR connecting system. Some of the good services provided by synchronous machine is no longer there, like inertias, like the fault level support. So if that IBRs can behave like synchronous machine, maybe some of the problem can be resolved. So that's what we started our work on the grid forming development since 2013. I mean, in the last 10 years, we've been working on this subject. So around 2022, we published the world's first grid forming technical requirement in the grid code that would just define our requirement of the grid forming, how it should look like and what sort of performance requirement looks like, and how to actually demonstrate the compliance of the grid forming and also the modeling requirement for the grid forming as well. So since that development, we then published another document called best practice guide. And so a lot of the people in this room has been involved in that development of that guidance. So we expanded a bit further to say what we actually means in the GC0137, giving some examples and further different tools you can use to developing the grid forming technology. So currently another piece of work ongoing, just try to moving this one further. We're thinking about if the grid forming is such a good thing, is there any argument we can make to say we should mandate it for transmission connected generation? When we say mandated, there might be a certain element to say you have to split the grid forming requirement into what we call essential requirement and enhanced requirement. Maybe some kind of enhanced requirement should be really get paid for as a service, but the essential requirement should be there to provide the backbone or stability, to assure the stability of the overall system. So since we developed the technical requirement for the grid forming, for the people to get into the market, there should be a market mechanism for them to be participating. So that's the reason we actually went through a Pathfinder process. So how it works is that we've done a lot of system study. We identify the different system needs in terms of the inertia requirement and in terms of the system strength requirement. Then we go to the market, we publish all this requirement to say, this is what we actually need to support our system from stability point of view. And if you have product or development, you can think you can meet all this need. This is all the technical requirement has been laid out in the tendering document as well. You can bid into that process. So the contract is going to be a 10 years contract, but you have to maintain a minimum level of the system stress inertia and fourth level to help the system. So basically you have to guarantee that it doesn't really matter what type of the operational condition you will be in. So when through the 3 round of the stability Pathfinder, I think interesting one probably is going to be Pathfinder phase 2. We actually have a 5 grid forming battery, won the bid, and this month we are currently actually commissioning one of our first grid forming battery in Scotland. So market arrangement should be a dynamic thing rather than just we done the Pathfinder, then everything finished. So when we're talking to the stakeholder, it's always a feedback to say, okay, you've done this Pathfinder, but is there any way you can make it much more flexible? Because of some people might want to run their plan quite differently. So whether that rather than just only have a longer term market, whether they should have a medium term market or day ahead market for stability type of services. So that's what we've been currently doing with the industry to develop a medium-term year -1 market. So effectively, we are procuring the inertials from the system so that need to be ready from September 2025. And in the longer term, we are looking at a day-ahead market, especially for some battery developers, if they actually want to change in the way how they run the battery. Maybe in the short term, they can provide additional services, especially inertial services to the system. We should be able to enable that. So when we're looking at overall frequency, how we actually control it, I touched upon the inertial element. I think another element is also that about frequency services as well. The Zhou mentioned about so experience in California as well. I mean, from our system, we just so we design the whole, we redesign the whole frequency response services as well. So the currently product we procure from the market, it's going to be required a much faster response. So generally, we are looking at people to respond within the 500 millisecond and need to be get that delivered within the 500 millisecond as well. So effectively, when there's a frequency drop within the 1 second, they should deliver the full response to support the system. So that's coming from the system service point of view and how to actually using the code and the market arrangement to facilitate the different new provider or innovation into the system. Another element we also think is very important is about enhance the monitoring system. So as we all know that traditionally we have all this SCADA system, we have all this current and voltage, you might have a P and Q element, we know the loading. But some of the additional characteristic of the system has become very important. One of the elements is about inertia. We can calculate it if we have a model, but how we actually measure it, that's become quite important for us to know currently where we are in terms of the system inertia. So we have 2 systems currently running in the NESO. We have a GE system just using sort of a passive PMU-based measurement. So we have a reactive technology system in the system as well. It's been actively probing the system and try to measure the response from the system to calculate the system inertia. And the bottom one is reactive technology, the damping measurement system as well. Some of you might not know that with more and more IBR connecting the system, we're actually starting to see different subsynchronous oscillation event happen in the system. So it's become quite important for us to know that what's the current status of the system in terms of the damping performance. So for us to take in the right action or mitigation in there. So the 2 important things I mentioned, one is identify system needs, making sure we have a right policy or grid code and market framework in place. Another element is that we need to have a good measurement or monitoring system in place. The third element is we have to have a much better modeling capability in the system for us to looking at all these different type of issues. And since 2019, we have this loss of the load event in the system. We're putting a lot of emphasis on to get a much better EMT model into the system. So we got a gray code change approved by the regulator for any of the new generation. If they connecting to the system after September 2022, need to provide a detailed EMT model to us. So we recently published the EMT modeling guideline as well that laid out all the details about different tests you have to do, different requirement in that modeling or validation you have to do before you submit that into the NESO. And at the same time, we also work together with our transmission owner colleagues, develop the whole GB system EMT model that shows up on the right-hand side as well. So the longer-term idea is that we are building this network model. So once we received all the new generation, so we are going to putting them into that big model. For the existing generator, we're currently doing another gray code modification to apply the EMT requirement retrospectively. So when we identify the need for the particular existing user model, we will go back, ask them to submit the model. So overall, that's a modeling development. So apart from that, we are starting to looking at different tools development as well. Once we have right EMT model, how we actually then developing the tools then for us to better use the EMT model to give us right information. I think the one particular interesting one I want to mention is that the last one is called Grid Connection Simulation Tools. As we know that the system getting much more complicated when you have a new generation, try to connect into the system, a lot of time you starting running into this control interaction type of problem. But it's going to be very difficult to exchange the right information between us and the user for them to do the full evaluation of the impact on the existing system. So we try to create it's more like a platform. So within that platform, we have all the existing system model with the user submitted EMT model. So for this new user one connecting system, they can directly connect into that platform and running all the control interaction type of study to give us assurance that they were not causing any additional issue before they connecting to the system. So that's overall what I covered. So the three things, system needs going to be very important, and we need to have a much better monitoring system. We have a much better modeling system as well. Thank you, Julie.
Thank you. Thanks, Xiaoyao. And this was actually excellent lead into our next presentation, which is from Jacob Kravits, and he'll be talking about the survey that they've done and looked into needs for different tools for system operators with high shares of inverter-based resources. And Jacob is a research and development lead in encoord. Go ahead, Jacob.
Hello. At encoord, we often think about, discuss, and sometimes even argue about the expertise needed to do generation, transmission, and distribution planning. And as the R&D lead, it's sort of my role to think about expertise. So in preparing for this conference, I wanted to kind of estimate what's the expertise of this conference. And we've had record attendance, so I think we're like close to 300 people here, and so hats off to ESIG. Let's say on average, I know it's average, I don't want to offend anybody, it's an average. Let's say there's each one of those experts put in 15 years, and then they're putting in 2,000 hours per year. I multiply all that together using my handy dandy reverse Polish notation calculator, and I get 9 million expert hours. And I did some research and compared that, and that's roughly the amount of time it took to write like Windows 98, so like a big project. But I've been thinking about expert hours a lot, because earlier and throughout the Q1 and Q2 of this year, we were doing some market research, and we were interested in how are people assessing reliability today, and how are you assessing reliability in 5 to 10 years? And really, that 5 to 10 years, that's where we're talking about those higher penetration of inverter-based resources, the topic of this session. And we wanted to make sure we were interviewing people across a diversity of roles and or organizations, the people who are actually clicking buttons on software, the people managing studies, the people developing new software. And I think we did a great job of sort of capturing some diversity in those roles. There's some housekeeping here. So each one of the interviews we did was 45 minutes to an hour. And what we did is we took notes throughout each interview, and then we had like a rough set of topics and questions that we were following to make sure, we sort of had some consistent data collection. After we did a sort of meta-analysis of what people talked about and tagged all the common themes. Just a note about sort of privacy for this stuff. For this presentation, we're not going to be sharing any direct quotes, and we can't share the actual organizations that we interviewed, but we're going to sort of share some of the general themes and challenges that were expressed to us. Now, we've talked about a lot of challenges during these interviews. And one of the most common challenges that came up was this idea of inverter-based resource, or a source that is controlled by an inverter. How do you interconnect them to a system? We actually just saw a slide about how this can often be a big challenge. So from these interviews, a lot of people are still doing infinite bus methods. So instead of representing the entire system, you'll just say, hey, as just a first pass, I'm going to represent my entire system at really just that interconnection point. And that's a really great screening tool. For systems where you needed a little bit more detail, people would run a phasor domain model. And that's a millisecond resolution model that's really capturing the underlying physics of spinning generators and some of the basic controls. In systems where you had a lot of inverters, you do what was mentioned before, was mentioned in the last presentation, a waveform simulation, and that's a microsecond simulation. That's you would call it an EMT, an electromagnetic transient domain simulation. But there are some challenges with doing a system-wide EMT analysis. And so we found out, what are those challenges? Perhaps the most consensus was around the input data. So 70% of the people we talked to said that it was really hard to just get the data needed to do EMT, system-wide EMT analysis. And we actually heard about that in the last presentation. Sometimes it can be an onerous task. And even once you get that data, validating it can be just as hard. So even if you have some sort of ground truth data, it's really difficult to understand if your model is actually representing what these devices are doing. Why is it so hard? Well, basically the physics of inverter-based resources permit this wide range of design. And so, yes, there are some fundamental building blocks to inverter-based controllers, but a lot goes into those building blocks, and you can kind of rearrange those building blocks in many different ways. And so gone are the days of maybe tens of standard generator models that we can just parameterize and sort of throw into our model and call it a day. We're really in this new realm where because of the proprietary nature of these models, a lot of the people we interviewed just said it's a really hard challenge to figure out input data. Another challenge that people expressed to us was this idea of more detail is needed during certain operating conditions. And this sort of makes sense, right? So in this top left-hand plot, we're showing a system response. And there's actually two lines here for those in the back. There's a green line and a red line. The green line is a phasor domain simulation, and the red line is that EMT simulation I showed before. And you can see the two lines, they basically overlap. So by doing an EMT simulation when you don't have a lot of inverters, you're not really gaining anything. But if you have a high penetration of IBRs, you see that red line, it has all these subsynchronous oscillations. And so there's really a lot of value in doing that EMT simulation. I think there's a lot of consensus around this, and I think there has been for some time. One thing that was particularly interesting to us during our interviews was this idea of more detail needed during space. So it's space and time. And so this is this idea of, let's say I have a 17,000 node system, and I have these different PV plants that I'm showing in green here. Maybe there are certain pockets of my system where I can do an EMT simulation, and certain pockets of my system where I can do a phasor domain simulation. And maybe those pockets change throughout the time depending on certain operating conditions. So there's sort of two dimensions here. Another challenge that we heard again and again from 60% of people was that the real barrier to EMT, system-wide EMT simulation, I want to be clear on that, system-wide EMT simulation was not computational, but it was cognitive. Now, I was expecting kind of some gasps there, so I'll say it again. We interviewed 41 people, and 61% of them said, the problem isn't about these simulations running faster. It's about a human's ability to understand and unpack that data and make meaningful insights. Any gas? Come on. Oh, yeah, good. I'm never getting invited back here. So I did a back of the envelope calculation here. Let's do a 3-phase point on wave. Let's say I have a 100-node system and I run a 1-second simulation that produces gigabytes of data. Extrapolate that out to a 100,000 node system. I get terabytes of data. Now, some of the data scientists, people are saying, well, we have algorithms. And we do, right? And so we can do like a fast Fourier transform, and that's what's being shown here. You can sort of see what are the harmonics, and we can, process terabytes of data. But algorithms aren't perfect. And sometimes it takes me like 20 minutes to find a show on Netflix because the algorithms are not great. And sometimes it's really hard to distinguish numerical noise from results. And sometimes when you're doing this with terabytes of data, you're getting a lot of these false positives. So things that are numerical noise, the algorithm says those are instabilities in your system, and you still have to manually go through and figure out, oh, actually, those aren't instabilities. I just have a solver that's kind of struggling, or an algorithm that's kind of struggling to capture some of this data. Now, there was a really great slide in the last presentation that talked about the inertia of their system. But we also have inertia. This industry has some inertia. And that 9 million expert hours that I mentioned before at this conference alone, that's been developed and honed over decades, where it's about tool A doing analysis A and tool B does analysis B. And in fact, because there's this one-to-one thing, you almost think about the analysis as the tool. So like I don't do an analysis, I just run the tool. And so a thing that we heard from about half the people we talked to is it could be really helpful to rethink this and think about, well, maybe the analysis that we want to do is actually spanning a few domains. And there are tools that maybe span span across those domains. But it's really important to allow us to become a little more flexible and think about the analysis that we're doing and the domains that we want to use to answer those questions, rather than just the tools alone. There are some other viewpoints that we think are worth presenting here. There was not like really consensus around these, but I think it's just a cool thing to think about. And I have the mic, so here you go. Device and model standardization. So I talked about proprietary models. What if we standardize them? Well, that's really difficult, right? Because a huge competitive advantage you have as somebody making these inverters is your controller. But maybe there are some ways that we could have maybe a test-driven thing. So, if as long as your device responds to certain or can pass certain tests, we incentivize that behavior by giving you priority in interconnection queues or something. That was one example of a thing that we heard. So it's definitely, there's not consensus around how this would be done, but it's a really interesting thing to think about. On that same level, grid forming in inverters, this has been another hot topic around this workshop this week. Maybe they absolve the need for some EMT level detail. And this is, again, emerging research. And so the assumptions of when this is true is maybe not fully understood yet. And, it maybe isn't a best practice, but it's certainly something that could show a lot of promise. So I've talked about the challenges so far. How are people actually doing this? So when we talk to them about how they're actually handling this, most practitioners we talk to were doing some sort of iteration between an EMT model and a phasor domain model. So they were passing information back and forth. And the people that we interviewed, they really liked that you sort of had some engineering judgment. You got to understand, because you were doing that manual process, you understand your system. And we're engineers, we understand our system, right? The people that also did this said it was kind of a pain, right? Because these commercial tools, they weren't really meant to talk to one another. And so we're kind of making them bend over backwards to pass these assumptions. And it can be really clunky. More on the research realm, maybe not as much of the industry people that or maybe not as much of the practitioners that we talked to, talked about these analytical methods. And so basically you could give the response from your phasor domain, from your EMT, give this into a analytical method, and then it can tell you sort of which part of your system you should model in phasor domain, which part you should do in EMT. It's nice because you get a single answer, but how much do you trust that answer? And maybe you have to rerun this. And so we kind of end up back in the same thing where there's a human who's looping these methods, and you sort of end up in a similar boat. Another really nice, set of emerging techniques are what we're calling pre-screening techniques. And I think we're even going to hear about some of these kind of methods later in this session as well. But this is basically some pre-processing you can do, and then you can have a maybe simplified EMT model or a more informed phaser domain model. And this is really nice because it's sort of the trusted models that we all have come to know and love over 9 million over our collective 9 million expert hours. But these maybe aren't as widespread, and they're mainly used with in-house tools, or in-house scripts. There's also some other domains. So I talked about the separation of tool and domains. Well, that's here because there's some other domains of analysis, and we're actually going to hear a really nice presentation at the end of this session about some different domains. All that being said, what we did hear from people is that linking existing software and existing tools is becoming exceedingly difficult and maybe even impossible. And so it's something we really need to address. And at encoord, we're addressing it by really kind of revisiting this idea of hybrid simulation. And where we're doing this is with a National Science Foundation Small Business and Innovative Research Grant. And we're in the phase 1 process now. And by doing that, we think you really address some of those input data needs with these hybrid approaches, because you no longer need high resolution input data. You can sort of target your analysis to what you're interested in. This idea of changing in space and time, well, we're sort of taking that to heart, right? And so this is the idea that maybe there are algorithms that as the simulation runs, it can sort of auto-adaptively figure out which pockets of your network are best modeled in phaser domain, which are best modeled in EMT. And then in the reporting sort of phase, it alleviates that needs of maybe terabytes of data that need to be sifted through algorithmically. And I'm proud to announce that we're sort of in the final phases of phase 1. It's sort of a funny sentence to say. We've been spending the last 10 months writing from the ground up a EMT level solver and a phaser domain solver from our own source code. And we've been having a lot of great success actually doing some of this proof of concept analysis and and showing that you can actually have algorithms that do this. Wrapping up here, I just want to highlight some of the consensus around data, cognitive overload, change being hard, and some of the highlighted views around model standardization. In closing, I'm reminded of an interesting quote, and I'm gonna give my source of this quote as Robert Kennedy because we're close to the Cape, and I think the actual origin of this quote is sort of unknown. But the quote is, "May you live in interesting times." And it's meant to have a positive connotation and a negative connotation. And I think it says a lot about where we are as an industry. It's up to us to figure out if this problem of assessing inverter reliability with high inverter-based systems, is this going to be interesting in a good way or a bad way? And so on that note, I hope you found this presentation interesting. And I would love to talk to you about it more. Please visit our booth. I look forward to answering the questions, and thank you for listening.
Thank you, Jacob. Very entertaining presentation, and definitely not a cognitive overload. So you're certainly coming back sometimes to present more. So next on, we're kind of shifting gears a little bit for a short while. We will come back to tools in our last presentation. But now you heard both Xiaoyao and John mentioning also changing needs for system services. And so that's what Matt will be talking about. So Matt Richwine, who is co-founder of Telos Energy, will be talking about this project.
Great. Thank you, Julia. And yes, while I'm presenting this afternoon, I'd really like to recognize it's part of an excellent team here that we have working with Julia at ESIG, also EPRI, Deepak and Sushrut, who are here, Nicholas Miller in the front here with Hickory Ledge, and Andrew Seiler also at Telos. And this has been a part of a project that's been running all year. We presented part of this in April at a webinar through ESIG. There's a few more details here, but I'm going to jump in and give just a brief background of what we're trying to do, why we think it's important, and then share some of the latest results and things that we're starting to see as we wrap up towards the beginning of next year. The key questions for grid stability services are as follows. So what services do we need? How much do we need? How fast do they need to be? And where do they need to be? And breaking those down, what services do we need? There's been a lot of great progress here in the industry, and that is not so much the focus. There's been lots of buckets, lots of qualitative discussions and descriptions of services. And so we kind of have a lay of the land, but I think one of the pieces that we're really trying to focus on here is quantifying these and quantifying them in a way that is generalized, technology agnostic, and repeatable, so that we can build a framework that can be rolled out to all system operators and planners, where we're not going to be stuck in any particular technology vein, that anything that can provide a useful service to operating an AC power system can play a role and can provide that. And if we can measure how much it provides, then we can go on to understand, okay, how much does the system need, and do we have enough or not? One of the things in this presentation, I think I should apologize in advance now, is that I'm going to say some things that I probably don't really mean. And hopefully not like the embarrassing at a bar kind of thing, but I'm going to say a word like inertia. And I don't mean it in terms of it's a rotating mass necessarily. We're going to try to talk about these in a more technology agnostic way, but understanding that inertia is, a word that's not going anywhere soon, but we're talking about it in the sense of a service that is not necessarily coming from a rotating synchronous machine. So on stability services, the overview of these is we're thinking about it in terms of a provision of services and a need for services, so much like a scale. And also with the need for services, it's combined with the acceptance criteria. So for instance, if you have a system and you have sufficient provision of services, which all of our systems should and do today, that's going to outweigh the need for those services and also the level of acceptance criteria. If you increase the level of acceptance criteria and kind of tighten the tolerance on the performance expectations, you could maybe not have enough services for those. If you increase the need for services, stability services, mind you, contingencies, for instance, you may not have enough. Or if you retire or decommit some of the resources that are providing those services, you could also have a problem. And so we've looked at this in 4 major pillars, one being the power type, so active and reactive, the time frame at which these are provided, the location where these are provided, and then acknowledging that grid operations has a role in the changing grid, depending on how much headroom, for instance, you have in any given resource, may affect how much that resource is able to provide those services. And so I'm going to go through these in a little bit more detail, but again, just also mentioning what can provide these services. We're talking about all resources can provide many or can provide one or more of these services. And it depends on the resources characteristics and operation. And, this isn't intended to be a comprehensive list, but we're talking about something that fits with synchronous or inverter technology, energy or non-energy types of resources, generation or load, distributed or centralized, everything can play a role. And what will change is how they're quantified, what role, how fast do they play, where might they be located, et cetera. Also to acknowledge, and this is something that we're still getting to, is the role of transmission here. It's an indirect impact to services. It is moving and delivering these services to different locations on the grid, though maybe it's not a provider of services in the way that we're framing this here. So what we've been really working hard on over the last couple months is testing this framework. So we've developed it, and now we're saying, okay, how does this do? How does it perform? And as such, we're doing that on a large system data set in the central US. Southwest Power Pool has been very supportive in terms of providing their data set and assistance and guidance to help us get going. And so we're taking that data set and we're exercising and we're applying the framework and exercising this. That data set we're talking about here is the power flow data and dynamics data set. And what we do first, and we'll go through each of these in a little bit more detail, is focus on the location aspect of it. And so this regional grouping analysis is where we break the system into a few groups to understand basically how those services, the need and provision for those services is in a group, and kind of extract that to a slightly higher level to make handling this full system data and all of its detail a little bit more manageable. That feeds into the provision of services, an analysis of the provision of services where resource by resource, we go through and assess how much of each of these services is being provided by a given resource. Similarly, we look at the need for those services. We look at the contingencies in each of those groups. And the output of that would, again, back to the scale analogy, we would be able to weigh the provision of those services against the need for those services and the acceptance criteria. And that being, kind of as Jacob alluded, kind of one of these methods of a pre-screening to see, do you have a problem? And can you, in a way that we think can be evaluated quickly to help scan the breadth of the future scenarios and different operating conditions and different resource mixes that we might see. And so to see how that performs, we're benchmarking it against a more conventional approach with a large system time series simulation. So conventional stability analysis, which we're doing in the phaser domain. Zooming in briefly on some of the parts of this analysis, beginning with the regional grouping analysis. So our objective here is to group not by historical ownership boundaries. The area lists that you would see out of these databases is not what we're using, but we really want to look at the electrical attributes of the system. And that includes both topology and resource characteristics. It's not just an admittance matrix. And by that, we want to carve up the system into places that perform dynamically similarly. And so beginning with the system data, we plug in, we do an evaluation of an interaction factor among all of the buses, and we apply a hierarchical grouping algorithm to take all of those buses and basically start to cluster the ones that are very close or going to behave dynamically similarly. And we get down, and in this case, what I'm going to show you is for this roughly, Kansas-sized region, we're defining about 8 groups. And with those, we get these regional groupings, and it kind of simplifies and helps us to assess what is happening in these different locations. And then we can also see how those relate to each other. Briefly, spatially, this is what it's looking like in this example where we're demonstrating it. These shapes are kind of loose, so bear with me on, these funny looking polygons. It's not exactly how it falls, but it's how we can represent it easily. And so we've got 8 different groups with different levels of resources, different technologies. Some are fully synchronous, some are mostly IBR, and in between. And they have some connectivity, which I'm representing with these green lines and the thickness of those green lines. And so we can see how this region is connected and how they'll behave. Switching up to the resource characterization or the provision of these services, what we're looking at is the list of resources, and we're checking to see, okay, are they online? How much headroom do they have? Is there some capability there? And then we're looking at the timeliness of delivery. So if they have the capability to deliver the services, how fast do they do it? And we've defined a few different timeframes, like a fast, a medium, and a slow. For now, we're going to focus on the faster and the slower timeframes. The fast timeframes being associated with, again, what you would see from a synchronous machine in terms of inertia or a grid strengthening responses that happen in the first 100 or 200 milliseconds or so after a dynamic disturbance. The slow timeframes are everything slower than that. More conventionally, it's your plant level controls, it's your excitation or governor system. Medium in between there, but we're frankly still getting there in this analysis. So the approach that we've taken to resource characterization is one of looking at it in a frequency domain analysis, as well as validating it in a time domain analysis. And going through this relatively quickly, what we're looking at is perturbations in terms of frequency and looking at how much active power is being provided in those different timeframes. Similarly, on the reactive power side, a perturbation in voltage and checking to see how much reactive power is provided by a resource in that response. And so these plots on the left are showing the frequency domain view, and on the right showing the time domain view to benchmark that. When we do that for all of these dynamic models in the region, we can quantify the provision of that service, so active or reactive power, and in its respective time frame, and then we can aggregate those up by group. And when we do that, we're starting to get data coming in like this. And so on the left here, we're showing the online resources of those in those groups by technology type, and also showing some of the services. I want to point out just one or two quick things here. You can see, for instance, groups 5 and group 6, they're largely comprised of synchronous machinery. You can also see that kind of in the middle with the fast active power and fast reactive power services, you see that there's most provisions, and it kind of looks similar to what you see from the synchronous machinery. This is what we would expect. Conventionally today, those fastest services are largely coming from synchronous machinery, and not so much from the installed fleet of IBR, which is largely grid following. Of course, we know we're on the cusp of a change there, a substantial change with the introduction of grid forming inverter technology, subject to how much it is adopted, hopefully a lot. The need for these services, then we're looking at contingencies. And so, for instance, loss of transmission in a group or between groups and loss of generation. And we're monitoring the dynamics that we see on the large system. And so some preliminary results that we're seeing, I want to zoom in on a couple loss of generation events. In this case, we're considering, and these are two separate events, a loss of generation, the red generator shown here in group 5, and then a loss of generation, this one is smaller, but still the largest in the group of group 3 that's coded in orange. And the red one is about 1,200 megawatts. The orange loss is about 600 megawatts, or about half or so. What we see is what I'm showing here is just the very beginning of the system frequencies in each of the groups as a response to the loss of generation. And initially what you could see is there's a couple things that are happening. There's a common mode frequency response with the trend of the whole system. But in that, you can see these layers of the responses of each of the different groups and how they're responding to the event. And it's not all the same. And so from the common mode standpoint, you can see that the larger unit, the loss of the larger unit has a higher rock off of the common mode, which you would expect. It's about twice that of the rock off of the common mode system response from this smaller generator. So yes, you're hitting the system twice as hard. That's about what you would expect. But what you can see is the individual groups take a different ride on these. And in fact, you notice on the bottom graph, you can see that several of the groups actually have a local frequency excursion and quite high rock off that exceeds that you saw from the loss of the larger unit. And so that's an interesting indicator that says, okay, even though this contingency, the need for the service it was not as great, based on the location at which it happens, can actually stress that system locally more. And when we look back to the services provisions for those, you can also tie that to why. Well, some of these groups that are experiencing this higher stress do not have as much provision of this fast active power service. And these are the things that we're trying to tease out in a way, again, that is quick and repeatable. And so this is, there's similar work that we are undertaking on the slower services and also on the reactive power services around those. So wrapping up here, where do we see this used? Well, we see this as the ability to highlight in future scenarios and resource portfolios where there may be weak pockets, where you're lacking sufficient services of one variety or another. It can also be used to inform transmission investments, where new transmission investments may be located to, for instance, support weak pockets from stronger pockets. You could also use it to identify if there are potential plant retirements. How is that going to impact the balance of the stability services that are being provided? Similarly, with grid forming inverter technology, if this is to be deployed, where strategically might it have the most benefit in terms of providing these additional services? And also show how, there's a lot of different changing grid operations, and are there points even within a season, within a week, within a day, where the operations are changing in a way that's changing the provision of stability services and creating, for instance, a new pinch point. So we're finding that this framework is a fast way to understand large system stability risks. It is not intended to replace dynamic simulation. Model quality is still a foundational aspect of this. It continues to be a challenge, and we see lots of applications for this. We're excited to continue this and test it for higher IBR futures, and also evaluate the impact of transmission and GFM technology using this framework. So on that, thank you. Sorry for running a few over.
Thank you, Matt. All right, so last but not least, from far away in Australia is Behrooz Bahrani. Behrooz is associate professor at Monash University, and he'll be, again, we're coming back to the tools, and he'll be talking about one of the tools in a toolbox that is kind of gaining more interest with high IBR.
Thank you so much. Victor. Yep. Oops, what happened? Okay, cool. Okay, thank you so much, Julia, for the introduction. Well, as the last presentation of the day, I'll be talking about another tool in the toolbox. So I'll be talking about small signal stability of particularly black box IBRs. And I'll talk about a frequency domain tool that you may have heard the name, impedance-based stability analysis. You may have seen this figure in other presentations, figures, reports. This is a figure that shows some oscillations that happened in Australia back in 2022 in West Murray region, a big part of the network in Australia. And AEMO in Australia tried to pinpoint the source of the oscillations. And after lots of investigation, they managed to understand what's happening. And there was one of the IBRs that was causing the issue. And one of the tools or concepts that helped them a lot was frequency scanning or impedance-based stability analysis. Well, today I'll be talking about that concept. I'll give some motivation and background and talk about basics of this tool and also, this concept, and also a tool that we're developing at Monash University to help the industry to do such analysis. But let's start with some basic background. Well, that oscillation that I showed earlier, that's not the only oscillation that has happened in different grids. There's so many actually oscillations. The list is pretty long, and this list is not an exhaustive list. The two red ones happen in Australia. Well, they don't happen only in weak or stronger. They could happen anywhere, and their exact source is typically not very easy to pinpoint, but typically they're somehow associated with inverters. And well, not so good for energy transition. They can slow down things. We don't want them. And unfortunately, a lot of grid operators reactively identify and manage these oscillations. So they're emerging as a big risk. We don't really want them. We want to know what's happening. But what are the motivation that we want to use such techniques, such like as impedance-based stability analysis? Well, like I said, IBRs are growing. We are using them anywhere, and they're kind of challenging stability in the grid and bringing oscillation risks. Traditional tools we've got, they're not really good to understand and analyze such systems. Typically not very good for black box IBRs as well. And impedance-based stability analysis, on the other hand, can be a very interesting, insightful tool that can help us actually work with black box IBRs. That's a big advantage of this type of analysis, and is rather scalable and give a lot of insights into operations. But let's have a quick look at the existing tools and see why they're not very good. Well, EMT, I guess we had a number of talks about EMT. They're very accurate, they're very good, but very time consuming. They're not really easy to scale and very difficult by looking at time domain results to understand what's going on in your system. It's kind of impossible. State space analysis, well, very, very suitable for oscillation detection, understanding what's happening in the system, but you know, they require linear models of your system. You need to have a lot of insight. You need to know, actually, you need to have a white box model. So they're not compatible with black box. And harmonic analysis, well, it is used in certain jurisdictions to do certain analyses around harmonics and frequency, but they are very limited in scope, and they're not really fit for purpose for control interactions. Well, impedance-based stability analysis can be a solution. Well, it is faster, typically scalable and insightful, particularly when it comes to black box IBRs. Like I said, you don't have to know what is inside. After this brief motivation, let's go a little bit deeper into what this concept is. And I understand that we probably have some experts in the room around this topic, and probably some of us are not really familiar. So I very briefly review some basic concepts here in order to prepare us for the more advanced concept of impedance-based stability analysis. Well, transfer functions, probably everybody knows what they are. Transfer functions are essentially the relationship between input and output of a given system that you've got, and it tells you how the input is, how the output is essentially related to the input at different frequencies. And we typically represent them by Bode plots. They are essentially systems magnitude and phase, and they can help you identify resonance frequencies, stability margins, a very interesting tool. And oftentimes in our systems, we've got controllers, we've got feedback loops, which are used to maintain the stability or modify the response of a given system. And when you look at this feedback loop, we've got an open loop transfer function. Your controller multiplied by your system is the open loop transfer function. And you can leverage that open loop transfer function to do a lot of interesting analyses. The likes of Nyquist stability criteria can be applied to them. And that's the basis of impedance-based stability analysis. But what is Nyquist plot? Essentially, it's a graphical tool that you can look at, it can assess the stability of an open loop system, typically applied to the frequency response of an open loop system, and shows how you encircle the critical point. So if you are encircling the critical point, you're unstable. If you're not, you can actually conclude that you've got a stable system. So we're going to use these concepts in the impedance-based stability analysis and see how it works. So imagine that we've got one inverter connected to the grid, and you want to do impedance-based stability analysis. In a nutshell, the idea is to somehow identify or obtain the frequency response impedance of the grid and the IBR, and use some stability criteria, well, in this case, Nyquist stability criteria, to assess the stability. Well, you first need some sort of EMT model. Black box EMT model of IBR is very suitable for this. You can use them to obtain the frequency response of your system, and then use these frequency response of the impedance of the grid and the IBR, and interconnect them as per network topology, and do frequency domain analyses, again, like Nyquist stability criteria. Well, why is it effective? It is actually very good for finding oscillatory modes and also the stability of the system. But let's go a little bit deeper and understand how exactly we do it. So the system that I was showing here was essentially a SMIP case. So I am here representing it in a little bit more like a simple way. The inverter with impedance, and then the grid with admittance. And if I write some equations here, I can represent this system with the equivalent closed loop system at the bottom. And we can write this relationship between voltage and current. And when you look at that relationship, this Y multiplied by Z somehow resembles an open loop transfer function. So that's how essentially we go from impedance to open loop. So we write this equation and leverage this open loop transfer function that is in that relationship, and then apply frequency domain techniques such as Nyquist plots to understand whether the system is stable or not. And well, a lot of other frequency domain techniques can be applied, by Nyquist is actually one of the most well-known ones. So that's the idea. So if I want to categorize these different steps, step one is to understand your system, divide it into separate subsystems, and then identify the impedance or admittance of these subsystems, and then apply the construct the open loop transfer function or frequency response, and go from there and do a stability analysis. So this is one example in which we have identified the impedance of two inverters, and also we have benchmarked them against their analytical model to make sure that it is very, very accurate, and the procedure we've got is actually accurate. Then we applied Nyquist stability criteria, and we have changed the SCR of the grid, going from 2 to 5, and then we've realized that when we are going from 3 to 2.5, we are encircling the critical point, meaning that the system is expected to be unstable. And to the left, we've done EMT analysis, and it actually indeed shows that when you go from SCR 3 to 2.5, you become unstable. Well, use cases. Where can you use this tool? Well, obviously for control interactions, this is a great tool to diagnose and mitigate oscillations in multi-inverter systems. For earlier stage screening, obviously a great tool. When you want to add a new IBR to the system, you can use this to understand how system will react, or any other grid component. When you're adding to the grid, you can use this. Also for OEMs, when they want to tune their controller, this is a great tool to tune parameters or optimize the parameters of a controller. If you've got access to the impedance of the grid at the point of connection, then as an OEM, you can actually use this tool to do some control tuning. But like any other tool, there are limitations. Obviously, this is a small signal domain only tool. You are unable to use it for large signal events, for fault, islanding, or things like that. This cannot be used. And at the same time, some nonlinear effects in your system may be overlooked. So that's one thing to remember. It is an operating point dependent tool, meaning that if your operating point changes, well, you need to do another scan. And also, it's extremely important to have very, very accurate impedance extraction. It is very, very sensitive to accuracy of the impedance, the old saying of garbage in, garbage out. So you have to pay a lot of attention there. With all this said, let's have a quick look at what we've been working on at Monash University on developing a tool for this technique. Back in 2023, the Australian Renewable Energy Agency, or ARENA, funded a project at Monash to develop an impedance-based stability analysis for industry needs. We've been engaging extensively with two of our industry partners, AEMO and PowerLink, and particularly we wanted to make sure that we are matching features with needs. So that has been a very important part of the process for us. And we've been collaborating with them extensively. We've been collaborating with particularly AEMO more recently to make sure that the tool is applicable to their practical models and real systems. So in terms of timeline, back in 2023, we started, and the first version was introduced in 2024 February, second beta version in August. And we're hoping by the end of 2024, it will be available for wider industry use, pending all the tests with real systems. In July 2025, end of our current ARENA project, but not end of the tool. We are hoping to continue the tool in different, hopefully with different pathways. A closer look at the tool. So the way it works, essentially, it is for the moment mainly for PSCAD environment. So you need to put there is a module you would put in your PSCAD, and that module then interacts with an external application, and you can do the analysis there. So the first step is to set up your impedance scan module within PSCAD and give certain parameters there. And then you will obtain, or the tool will obtain time domain data from PSCAD, bring it to the to the interface, and it will scan the impedance for you. And we have a database approach there because we understand that in your system, you may need to do so many different scans or different inverters there. You want to have lots of data in the system to manage. So there's a very interesting data management strategy there. And after that, the last stage would be obviously stability analysis within the tool itself. A little bit about software development. It's a Python-based application, so the core interface and analysis are in Python, and well, of course, the ZAT module itself will go into your PSCAD. There's a trunk-based development, making sure that regular, smaller updates are introduced to ensure reliable improvement and reduce risk of large-scale issues. And particularly cybersecurity is very critical here, and we've been making sure that there's no issues from that point of view. So we've used Sync Scan. So Sync is actually a company that provides certain type of scans to catch vulnerabilities in your code and third-party libraries to, again, ensure cybersecurity. And continuous integration here, each code update triggers lots of automated tests to maintain stability and security. And we've been trying to stick to best practices for software development to make sure that the tool is at the highest possible quality. A very quick case study before we finish. So the tool obviously can be applied to SMIP cases, but also can be applied to larger systems, multiple inverter systems. In this case, we've got a 4-inverter system. The way to go, obviously, is splitting the system to a bulk network and plant of interest, so one plant at a time. And then you can do stability, different types of stability analysis. So this one, we've got 4 inverters, 2 grids following, 2 grids forming. And then the system itself, or the network, the rest of the network is a weak connection to the grid and some passive loads and STATCOM at the point of connection. So we have done the scans using the tool, and we've done, well, different analysis on this. We don't have time to go through all the details of the analysis, but in a nutshell, the scans show that all of these inverters can maintain stability, and all of them are essentially, for that operating point that we have examined, are absolutely stable and no oscillations are happening there. In addition to do Nyquist criteria, obviously, we are adding lots of other features. We are looking into closed loop and closed loop for the plant and also the system in order to understand the oscillation modes. There's certain information that you can actually deduct from looking at the closed loop system. These are all work in progress to add all these more readily available for the user. But already we can pinpoint some of the oscillation modes in the network and understand their damping and how well damped that particular mode is. There is also a very important feature that we are hoping to add in the short future. So it is essentially that operating point dependency, and understand how we can make sure that by a limited number of scans, we can have all the operating points available to us, but some sort of extrapolation, and making sure that we don't need to repeat scans for every single operating point. Because at the end of the day, scanning is the most time-consuming part of the tool. It takes time depending on what is the frequencies that you're interested in, what is the minimum frequency, how many of those frequencies you're interested in. That will determine how long your scan will take. On that note, I guess we can conclude the presentation.